Hello, 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 and good morning. All right, working again today on my TypeScript collections library. I am working on the binary search tree, and I pretty much finished the important parts of the implementation for the binary search tree. Today I thought I could do a little bit of performance testing, profiling, and compare it against other known collections libraries, JavaScript and TypeScript connections libraries, and maybe optimize some of the codes so that I am competitive with those other offerings. And okay, I started doing that a little bit yesterday in TypeScript. I want to do it straight in JavaScript now, and I am trying to remember how to do require imports. And I've been doing TypeScript for like so long now, and not straight JavaScript. I've been using the import syntax, the ES6 modules, and now I'm like, it's still experimental, right, in Node, so unless you want to have to use experimental flag and stuff and other, I think you need to use like a .mjs as a file ending. Anyways, so figured I'd just use the require. I'm a little rusty. So what does that give us? Binary search tree is not a constructor. Cool, 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 cool. Why is that? Let's see. What are you exporting in here? Export class binary search tree. Oh, let's look at the JavaScript. Exports dot binary search tree, type of binary search tree. Binary search tree is a class. Okay, so why can't I just type of import? Okay. Okay. Binary search tree is not a constructor. That's interesting. Alright, let's try something here. Let's come back to our ES6 style, TypeScript style imports. Alright. And let's make this a TypeScript file. Let's rename F2, right? Yeah. TS, like this. Yeah, we don't care about that. Okay, now let's just run TSC. It'll warn us about that, but it'll still transpile it. And let's look at what okay. It's got this complicated import thing. Import star, blah, blah, blah. Right. It's probably because the way I'm exporting, I'm doing the export. Instead of doing module export, I'm doing exports.binary search tree. Could that be it? Don't know. But in any case, console time. Yep. Let's run this. There we go. Okay. So what we're doing here is we are where are we? Yeah. We're just adding to the BSTs. We're adding 1E3, so that's 1,000 items. And as you can see, my competing implementation from Mr. Bassarat is a little faster than mine in terms of adding random numbers to the tree. What if we were to increase that to, let's say, 1,000,000 would be 6, right? Let's go with 1,000,000. Oh, I have to transpile it and then run it. Ooh. So mine is quite a bit longer. Once you get into more items. Took 1.6 seconds to add 1,000,000 items. The other one took 734. Let's run it again just to see if it could be much difference. No, it's about the same, right? Actually, his is like pretty much bang on the same. Mine, there's more fluctuations. Let's run again. That's interesting. His comes in steadily at 734. Hardly any difference. Mine fluctuates a bit more. Why that is, I don't know. Oh, this time it took a little longer, but alright, it's pretty consistent still, I mean. And my implementation is about twice as slow for 1,000,000 items. I have a feeling that it might be because I'm using, so we're only testing the inserting, right? The adding to the BST. My implementation is not, is it recursive? It is recursive, okay. It's recursive right here. I wonder if I try to implement it in with a, loops or something. What am I doing here? I'm just basically putting that in there, yeah. And if we look at how he does it, that could be interesting. Let's see. Binary search tree. Okay, add element. If this insert node, this create node, this elements, okay. So this is probably the one here, insert node. Insert node, probably a private somewhere. There it is. Okay, how does he do it? Yeah, I don't think he does it recursively, right? I don't see any other call to insert node. Nope. Right. So, yeah, there it is. He's using a while loop here, as opposed to my implementation that just uses straight up recursion. It would be interesting to see the performance I could get out of a more iterative, I guess, or imperative solution. So let's do that. Private insert imp. Let's call it that for now. Let's see if we can have the same API. I don't know how I'm going to implement this right yet, but it'd be nice if I don't have to change the API. I might have to though, but we'll see. And return a BST node. Okay. Now, let's try to find some inspiration in. Let me just turn that off. Okay. Let's look at here, binary search tree, searching, insertion. There you go, non-recursive. That's what we're looking for. Using a pointer to keep track of where we came from. Yep, all right. Let's put that on the side, see if we could I actually have to, I have to remember to return the root. So, okay, let's see, node walk root. Now this is a C or C++ implementation with pointers and stuff. Yeah. How does this work? Uh-huh. All right, what if I was to if the tree is empty, return a new node? Well, it seems to me that this would stay the same, right? But anyways, let's try to follow along the logic. So there's this, I think this variable here, they call walk of type node, BST node. It starts off being the root. Okay. Could also be undefined, right? And it looks like it should always be a node. am not... All these pointers, man. I'm not familiar with C or C++ pointers. Maybe I could try to find another implementation. So let's see, binary search tree. Insert. Let's take a look at this one. This uses recursion. Let's search. Oh, that's the search. Insertion. This is very similar to what I have implemented actually. But this uses recursion. And that's the only option offered here, so okay. Let's look at this one. Ooh. I think that's what we're looking for. Utility function to insert a new node with a given key. Node root. Let's look at what this looks like in Python. What? And that's C#. That's interesting. Okay, let's just stick with this one then. So what is he doing here? He's creating his new node. Pointer to start traversing from root and traverses downward path to search where the new node to be inserted. So node X is equal to the root. Cool. Pointer Y maintains the trailing pointer of X. The trailing pointer. Anyway, starts off as Y. Null. While X is not null, Y is equal to X if the key is smaller than X dot key, then X is equal to X dot left. Else if it's bigger, or actually equal. What if it's equal? That's whatever. X is equal to X right. And then you loop back again. Basically Y. You do that, and then you end up at the end with, okay, so basically Y is the parent. That's what they mean by the trailing pointer. I probably wouldn't need that. I already have a parent property on my nodes. But anyways, so that's how you recurse and get down to wait, how would that work? If the root is null, i.e. the tree is empty, the new node is the root node. Oh, I see. That's where you, okay. Yeah, because this would be skipped anyways if that's the case, so that's cool. If the new key is less than the leaf node key, assign the new node to be its left child. So you're comparing it to Y. Ah, okay. That's why you don't need to check equal whatever, because you, okay. I get it. If the new key is less than the leaf node key, assign the new node key to its less, yeah? Else assign the new node its right child. No, that doesn't take into account the case where they would be equal, doesn't it? It does, and I'm just not seeing it. All right, let's try to kind of replicate this, this implementation here. So if I was to do this, I'd start off with creating my new node, right? Oh crap. Okay, thank God for Control Z. Undo. Alright, so I already have my new node. I'm passing it in from the calling function, so that's cool. It's already there. Now I need to do, I'm going to call this current node instead of root. So let current node equals root. Instead of X, I meant. And now, do I need the parent? I don't think I need it, so I'll try to just skip the Y that they had. So while loop here, so current node, while current node, simple as that, yep. And then if new node dot value, actually new node dot is smaller or lower, is lower than current node. Yep. Then what do I do? Current node equals current node dot left child. Far so good. Else current node equals current node dot right child. Okay. Good, it'll keep going until we hit undefined, and then we need to deal with the parent. So if current node dot parent, possibly undefined, I guess that's true. All right, so let's do if, the good old if current node and current node dot parent Does not exist on type never. Wait, what? How am I getting type never for this? This is weird. Okay. Actually, it actually shows it as undefined. Well, that's interesting. It's equal to root. Wall current node. Ah, right. So once we're done with that, that means that current node is now undefined. So we do need to track it. We do need to track it. Alright, so that parent node equals undefined for now. But we want it to actually, we don't even need to do that. Let's just type it though. Parent node is going to be BST node of type T or undefined. And we might as well do this too. Okay. So now, as we're going down, the first thing we're doing here is setting our parent node to equal current node. Now, if parent node, okay. If there is no parent node, yeah, there is no parent node, then it means the root is empty, and we can just we can simply return the new node. Actually, now that I'm thinking about it, it doesn't really make sense to return. I'm gonna have to change that. Right. What does my add function look like? So let's make this, for testing purposes, a public. We'll call it directly. Okay. And then we might as well not pass in the new node like this and just create it right in here. We will need the value though, won't we? So that's just, it's about the same thing anyways. Except that if I'm calling this from, maybe I should wrap this. After all, I'm just going to make a public add imp value of type T, and you're going to call this dot insert imp, and you call this dot root, and new node, new BST node with value, and this dot compare function. There we go. That'll work. Okay. Now I don't need to return anything. Okay. Now, I'm slouching out of screen. Okay, so if there's no parent node, it means the root is empty, basically. So we can just if y equals new node. Oh, we are actually returning. Returns the pointer where the new node is inserted. That's interesting. Is it actually inserting it though? Oh, it is, okay. Well, you guys can't see, but maybe I should put it on screen and split it so you guys can follow along. Let's try that. There we go. Let's close this. We have wider field of view. Can get this a little bit narrower. There we go. Okay. All right, now, so if there's no parent node, where was I? If the root is null, i.e. the tree is empty, the new node is the root node. So I would do parent node equals, yeah, that wouldn't work though. Would it? And I don't see why it would even in this code. You'd just be, right here, you'd just be assigning new node to the variable y. You are returning it though. You are returning it. Let's see, driver code. Yep, that's going to help me understand a bit more. New node root, no. Root, insert root 50. Oh, I see. He doesn't have a separate node class. Oh, he does. What? Oh, but it's essentially a tree. It's essentially the entire tree. He doesn't have like a wrapping tree class, so I have to take that into account. The principle is still there though. I'm going to have to modify this. So if parent node is empty, and we can just do this root equals new node. All right, that should work. That's taken care of. And let's see, what's next? Else if the key, so in our case it's going to be the new node. New node. dot value. Oh, actually, I just go to new node is slower than our parent node. So if it's lower than our parent node, then we just need to go parent node dot left child is equal to our new node. Okay. Else, if oh yeah, and that's the thing, he's not accounting for if it's equal. Also, if new node, we'll test this in a second, if is greater than. Oh, he just has an else actually, so let's do it. Let's do it his way. I'm pretty sure that's not going to work for our implementation. Going to need to modify that. Because, you know, if it's equal, it'll still push it to the tree, but we don't want that. we don't want to have duplicates in there. Else parent node, right child equals new node. Oops. Okay. I don't need to return the pointer. Alright, let's take that for a spin, see what happens. Use Quokka. Cool. So let's just copy this. Oh yeah, and I have no. Where am I keeping track of the size? Is it in the wrapping? Nope, it's not. Although in this case I could. So this dot size should work here. Oh, that's not true actually. Because I don't want to add if there's already alright, so we'll hold off on that. And we're using add imp. Add imp, whoops. Let's just do this. That's interesting, okay. That's normal because I'm not updating the size right now. More interesting to see what our tree looks like. Let's see, it'll be easier to look at this here. Alright, our root of value 13, so far so good, has two children, and it should. One should be 10, one should be 20, so left should be 10. Cool. It is. We're not keeping track of the parent though. That is a problem. I'll have to get back to that later. And our left child should be 6 here. Yep. And 6 is a leaf, so it doesn't have any children. That's right. The right child should be 11. Good. Okay, so The left side of the tree works. The right side should be 20, that's right. And then we should have 18 and 21. So left should be 18, and this should be 21. Cool. So that works. Well, let's see what happens if I do bsd.add imp 21. Pretty sure we're going to end up with, there you go. So we've got our right child 21 also has a right child 21, and that's not what we want. That is not what we want. So let's, okay, let me look at something here. What are we doing to set the parent? Let's remove, where's my insert? Here it is. You know dot parent equals root. Okay, we're setting it here. So we're gonna have to do the same thing too. So when we're setting it here. No, we're setting it here. So that's fine. The root node doesn't have a parent, so that's cool. We don't need to touch that. But here we're going to have to do something to get the parents properly. Alright, so parent dot node dot left child is equal to new node, and obviously new node's parent is equal to the parent node. That's pretty easy. Do the same thing here. Parent node dot right child equals new node, so same thing, new node dot parent is equal to parent node. So that takes care of that. But what happens when we have something that is of equal value? We're not dealing with it in our recursion. Well, recursion. As we're traversing down a tree, we're not dealing with that, right? We're just going, if it's lower, then choose, boom. But really, we should short circuit the thing right here if we can. Because what happens if we get, okay, here's a silly example, but let's say we're trying to insert the same value as the root node, right? So right away should stop and do nothing. But right now, what are we doing? So the current node becomes the root. Cool. Now we're saying if the new node is lower than, it's not, it's equal. And then we go else, the current node becomes the children, and then we go down the tree all the way to the bottom, which makes no sense. So we need some kind of way to go if what is more likely? That it's going to be equal? No. In all likelihood, you're not going to try. I mean, most cases, you're not going to try to yeah. So let's do it that way. Boom. If new node is greater than, if is greater than current node, then current node is equal to current node right child. Now what? Cannot read property value of undefined. What are you talking about now? Well, that's interesting. Might have to do something with the syntax here. Let's just use this. See if that fixes our problem. It doesn't. Very interesting. I gotta do else. Else if. That was my problem, I believe. Yeah. So let's get back to what we had. And do else if. Else if. There we go. Else if the new node is greater than the current node now becomes right child. Else, so in other words, if it's equal, then the current node, no, see, that's the thing. Else, return. We don't need to do anything. We're not inserting anything. And what's our... Is add supposed to be void? What was my API? Was I returning something if it worked? And no, okay, cool. So let's keep going with that. So I think that pretty much takes care of the cases where we have duplicates. Where am I? Oh. All right. If there's a duplicate, we just return out of the function. We're done. No inserting for you. But then, if that's not the case, our parent node will be a leaf node. And then we go, well, actually, hold on. Just created a problem there, didn't I? Because what if the root is empty? Current node, parent node is equal to current node. If the new node is lower than the current node, and the current node is the root, well, it just won't go into this. It'll skip this. Okay, so it skips this. The current node is empty. It completely skips that, so we won't be returning. Cool. And then we can hit this here and set our parent node to the right thing. And we might as well return from this and not even... what do we have here? Else if, is it going to be evaluating this? No, it won't. It'll just skip it because it's else, right? Okay, so we're not doing extra work for nothing. I don't think so. Anyways, if I understand the workings of the else if statements. Okay, so I think we're in business now. This should have fixed our little duplicate problem. Let's take a look. So our root is 13, good. Right child is 20. Then we should see 18 and 21. So this should be 18. Right, and it doesn't have any children. That's what we want. Oh, also has the right parent. We fixed that as well. And let's just make sure that this is the right parent to parent is 13. Good. The right one should be 21. Cool. Parent should be 20. Yep. And it doesn't have any children. No duplicates. Yay! Let's just take a look at the left side too, just make sure we didn't screw up anything. Left should be 6 with a parent of 10. Good. And this parent should be 13. Yep. And then that's the left child. The right child should be 11. And the parent should be 10. Yay! Okay. So that's good. Now the only thing that's left to fix is the size. Okay. And we can probably, let's see, let's think about this here. We have to be careful because if it's a duplicate, we don't want to change the size. So we only change the size. Let's see, we change it in here because we're adding, so we're going to need to do this. Like that. And this not size, plus plus, basically the same thing. Actually, like that. I don't need to do that. Because in all these cases, we are adding one item to our tree. In the case where it's a duplicate, then we're just short-circuiting the whole thing. We're doing it right here. So we can just do it once and do size plus plus right there. And that should work. Should being the word here. Okay, let's do dot size. Yay! 7. Right? 1, 2, 3, 4, 5, 6, 7, and not 8 because that's a duplicate. But if I was to do 22, boom. All right. Marvelous. What if it's just the root? Boom. We're in business. We are in business. Okay. Now, I don't think I'll be needing this anymore. Not for now anyways. So let's get back to full screen. Yay. It can work. Breathe. What do I need to do? I can just stop Quokka. I can compile my TypeScript. Okay, and I can run, oh yeah, first I have to add this. So we're gonna call this const my imp BST. Alright, equals new binaries. Oh, actually, I don't need to do that. I shoved it in the same class. So all I really need to do is add this here. There we go. My BST imp. I'm going to call it for imperative. And we're going to use add imp. There we go. So again, I have to TSC. The compiling errors are getting on my nerves. Might as well fix them. So what's the problem here? Compare function A is going to be of type any. Well, actually, technically, what's the signature? What am I expecting here? I'm expecting this. AT, right. So T returning a number. Okay, so in this case then, we're just gonna use, let's just do that. Yeah, okay. Max is going to be a number as well. And I think that takes care of all our errors. Let's see. There we go. Now we're good. Let's performance.
1, 2, 1, 2, 3.
Aha. Okay. So our imperative add function is faster than our recursive one. But it's still a bit slower than our friend Bassarat's implementation. Interesting. And if we were to, for kicks, come back down to our 1,000 instead of 1,000,000. Can I do this? Save some time. I think I might be able to. Let's see. Yep. Seem to have worked. Oh, look at that. That's interesting. That is very interesting. With a smaller set of items, my implementation is actually quite a bit faster. Why would that be? Let's run it again just to... Same thing. Same thing. Can't help but notice that his seems to be more consistent, right? 246.8, 246.9. I get like 118 and 153, 29 something. So why is that though? Hmm. 15 something. 118. Is he balancing his tree somehow? Well, that could be the explanation, because this is just a vanilla binary search tree. Like, I'm not doing any balancing at all. So obviously, if for some reason, oh, I know what would be a good test. Okay, I'll test that afterwards. If the tree is balanced, if he's balancing the tree, his add operations would be a little slower per operation, slightly slower, right? Because each add would need to see if the tree needs to be rebalanced somehow. But as the tree gets bigger, you wouldn't have to go as deep into the tree. So you would save some time there. Not to mention for searching later on and removing and whatever, but we'll come to that. But in terms of adding it, it didn't occur to me that even with insertions, it could be for big trees advantageous to have a balanced tree. I didn't think about that, and that might be the case. Let's look at the implementation, see if we can find a clue that it's somehow doing something to balance it. Insert node. Okay, so what are you doing here? You got the parent, you got the position. Position is null, so that's basically what we got going on, right? Const CMP, this compare node element, position element. Alright. And he's returning, okay, that's basically the compare function that returns, 0 if it's the same. Or 1 if it's, yeah, that's what he's got going on. And the position, so yeah, okay. Else parent position equals position is the right channel. And what is he doing here? Node dot parent equals parent. Okay, he's setting the parent afterwards. It's not a bad idea. I can probably do the same thing here. Won't change anything in terms of performance. It will in terms of removing lines of code. Right, where am I? That's not the right one. Yeah, see, I was doing it here. Dot parent equals parent node. Parent node dot left child is equal new node, and they're pointing to the same thing. So I can indeed bring that right here. Like that. Get rid of this, and then we're back to our one-liners. Yep, get rid of that. Get rid of all this and that. Okay. Just make sure I didn't screw up anything. One, two, three, 4, 5, 6, 7, 8. Seems good. Let's see, just to make sure we've got our parents. So let's put it here. Okay. The root. How does the root have a parent? The root's parent is its own parent. That doesn't work. Okay, so let's see. Yeah. How does Z deal with that? Node parent, if parent not known. Node dot parent equal parent. If parent equals null, tree is empty, this root equals node. Uh-huh. He's got the parent as that's also what we have, isn't it? Yeah. If parent node equals root. Whoa, what am I doing? That might have been the problem here. Yeah, I think that was the only, yeah. That's a little dumb mistake. Okay, so we got the root. It's got a right child, and it has no left child. That's not good. They're all on the right. 20, 21, 22. And that's it. What? That doesn't make any sense at all. Wait a minute. Yet it's still showing a size of 8. That's because we're hitting this thing here every time. So if parent node, this.root equals node. If new node is lower than new node.parent. Oh. Come on, come on. Okay, so my implementation might not be as fast. Oh no, I tested it with the correct. So this is left. Okay, so I think we're good now. Parent is undefined. We got a left child, which is the 10. And it's got the parent, the root, yep. And it's got the 6. And it's got the 11. Parent is the 10, yeah. We're good here. Right child should be the 20. Where is it? 20, yeah. Parent being the root, yeah. Left child is 18, cool. Parent is 20. And this is 21. With the right child of 22. Parent is 21. Parent is 20, yeah. Okay, now we're good. We're good, get the right size, everything's good. Okay. So, okay. Now what? If parents well, this root. Else if this comparison is smaller than the size, then okay, so that's basically, this looks exactly the same as what we're doing. Well, that's very interesting. Very, 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 very interesting. I have a feeling. Woo! I have a feeling that is compare function might be faster than mine. First, let's run all of that again. Okay. Yep. Definitely faster. I didn't gain anything by doing that though, but I am faster for 1,000 elements. Not quite twice as fast, but not far. Very interesting. Now, of course, we're talking about like 1 millisecond for 1,000 elements, so, you know, that is like really micro optimizations here. But let's say for some reason we had a use case for something that was 1 million. 1 million. Boom. So I'm a bit slower. I'm taking a second. He's taking 0.7 seconds. Okay, so we've established that this is a faster implementation, so I'm just gonna console that out so we save a little bit of time here. So that's interesting. Let's find the sweet spot where we're kind of the same. Oh. Well, that's interesting. Quite a bit faster on this one. Let's run it again. Huh. Wow. Very interesting. So with 1 million, he's about, 75%. How would you describe that? I'm 30% slower, roughly. But with what is that? E5, 1E5. That's 10,000. No, 100,000. No, yeah, 100,000. So with 100,000 element, he's 3 times as fast, right? I'm 300% slower. Whatever, he finishes 3 times faster. That's weird. I don't see the pattern there, and about the same for 10,000 elements. And then for 1,000 element, boom, I'm faster. Okay, let's think about this. I'm faster for 1,000 elements or less, I'm gonna guess. Let's try it with well, basically 10. No, that's 100. Yeah, faster. Let's try it with 10. Quite a bit faster. Well, that's interesting. That's really, really interesting. It means it's like he's got some sort of setup. Something, anyways. There's a cost to adding stuff at the beginning for him. But as we get going and we end up deeper in the tree, then I start to lag behind. But then, as we hit 1 million, I start to catch up again. So let's try. We tried 1 million. Let's try 10 million. Now that's going to run for a little longer, but what the heck? Might take 10 seconds or something. 20 seconds total, I guess. Right, because 1 million was, I think, about a second each. So technically, if it's, there we go. So we've got 13 seconds for him. And what's it gonna be for me? This is so exciting. 19. So, not quite twice as slow. But yet slower. And I don't like it. I don't like it at all. Because the point of using a binary search tree, I would think, is when you do have a lot of items. Because if you don't, then who cares? And just use an array and the built-in sort function, right? So performance should be a concern. It should indeed be a concern. Now, how do I figure out where the slowness is? I've never really done much profiling and performance testing and stuff like that. Don't know where to begin. Like for the whole function, sure, that's pretty easy, but like, how do we explain the discrepancy? And let's think about this. Where can I gain performance in this? What's taking long? How do I figure that out? What am I doing in here? I'm just calling this, so that's not where the bottleneck is. All right, possibly the bottleneck is, like I was saying, in this here. Oh, well, duh. Yeah, that would definitely be a performance. So here's the thing. Okay, I think I found it. Well, at least part of it. He runs his compare function only once, gets a result, and then, uses that result. I'm using that compare function twice. Here and here. Yeah. So I'll see. I thought I was being clever by incorporating the compare function straight into the node so that we could do something that looks neat like this, like new node is lower than current node. Yay! But for performance, okay. Well, we do have access to that compare function in the class and the tree class as well. So I can do this differently, and I will. So we're gonna do it compare value. We're gonna call this compare value is a number. And it's equal to doing this dot compare function. We're passing in a, which is our new node, dot value. Oh, but here's the thing though. Here's my problem. Oh no, that's not a problem. Because the compare function is passed into the class and it's custom made to match the type, to compare the type properly. So yeah, I'm good. Doing that is fine. fine as long as, so new node versus the current node. Yeah, okay, right, new node dot value, that's what we need. So current node dot value. So we're comparing the new node to the current node, right? If new node is lower than compare value. So to compare value would be here, it would be higher. The new node is higher. No, it's lower. Okay, it would be, so compare value is smaller than 0, and then we do compare value. Compare value is bigger than 0. Cool. And then we can keep our this one here. Okay, let's run Quokka on this thing. Got the right size, so that's a good sign, but let's just make sure the tree's still properly built. Got ourselves a root of 13, a left child of 10. That has a left side child of 6. Its parent is 10, yeah. And then we have the right child, which should be 11. Parent is also 10, yeah, good. And we should have a right child here that is 20 with a parent of 13, yes. Left child is 18 with a parent of 20. And the right child is 21 with a parent of 20, and it has a right child of 22 with a parent of 21. Okay. We're good. Boop, boop. Okay. So the implementation seems sound. And I think we'll have gained some speed there. Ooh, that's exciting. Stop Quokka. And let's run our performance test. Should have started with something smaller, but we'll see. Okay, 14 something, 14 seconds for Basarat. And watch it, it'll be longer. Yeah, we didn't shave much, did we? We didn't shave much. Oh, one thing that would be interesting is to see if, let's see here, in our original recursive function, we're also doing that, right? Yeah, but I don't think that's the problem. Okay. Let's try it again with something a little smaller. A million, say. $732, 1178. So it's hard to say if we shaved some. Doesn't look like we did much, really. I would have to compare both implementations. I mean, I could. Yeah, why not? What the heck? See if it's worth it. We're gonna call this comp. And we're gonna do, basically copy this. Imp comp. Imp comp. There we go. And I just need to change my performance thing. Still okay. Let's use let's reuse this. My BST comp. Add imp comp. Okay. Let's do this. Well, let's start smaller with 1,000. See what that gives us. Oh, well, looks like we did shave some time off for 1,000 items anyways. Quite a bit if you look at this. Let's run it again. In terms of percentage, right? Of course, in terms of real, we're talking about less than a millisecond. And we are quite a bit faster. Yep. Okay. Let's bump this up to 10,000. Yeah. Twice as long and barely any difference. That is so interesting. So it means that, what does it mean? What does it mean? I don't know what it means. This is weird. Yeah, well, we are faster. Still twice as slow. Twice as slow. And we're getting to our million here. We're getting closer. And we are faster. It is a faster way to do it. Dare I do the 10 million test? I do dare. "14 seconds for Basara." 24 hours. The comp one. And it'll be probably a little longer for the other one. It's what? Faster? Okay. I have lost all confidence in testing. In performance testing and profiling. How can that be? How can that be? Wait a minute. That doesn't make sense at all. Oh no. Actually, I had this all wrong. It was slower the entire time. Yeah, I was looking at it wrong. Well, well, well. Wait a second. How does that even make sense? Why am I slower? Oh, it's probably because I have to make... No, I don't get it. Would this mean that it's faster to make this check here twice than it is to make this check once and then making this check here twice? But that's highly dependent on the compare value function that you're passing in, right? If you're comparing complex objects and your compare function runs very long, then it would be advantageous to do this here. Oh, this is kind of complicated. Huh. So that's a tough choice to make. But I mean, the performance difference is negligible. We're talking about, for 10 million items, we're talking about a 2-second difference. Oh, it's still 10% in performance. But I'm wondering how quickly that can evaporate if you have a complicated compare function. There's one way to test that out. There's one way to test that out. Let's have some fun. Let us make our compare function. We're gonna make it wait. Let's see. Let's do it like this. We'll just return that. But in here, we'll just do while. And let's do, let's just make it count to, I don't know, 1 million or something. 10 million. How slow can that be? Let's make it count to 1 million. See what that was. A while count. Yep. So while count. Once it hits 0, it'll break out of it. So all we need to do is do count minus minus. Let's try that and see what happens. back down to 6. We don't want to wait forever. Oops. I think a million might have been too much. Yeah. Big time. Yeah, I'm not gonna wait for that. Let's do it with, let's see, let's start with 1,000. So it'll be faster. All right, no, I'm so stupid. This is exponential. So let's just make it count to 10. Am I doing this right, or am I in some sort of infinite loop? Is that the problem here? While count. Okay, let's just be while count is bigger than 0. Let's go with that. Okay. So that didn't make much of a difference in terms of, so let's add. So it'll take 10 times as long though. Gotta keep that in mind. Oh, maybe not. Okay. Okay. And there we go. This is where we see that if the compare function takes longer, then our comp implementation is faster. No, it's not. Still not. What if we bump this up a little bit? Haha. Very interesting. They're still about the same. It's barely faster. I've got this thing. So it might not be worth it. Might not be worth it to optimize that way. Because it's actually slower for the cases where your compare function is relatively simple, and I would think that it often is, especially if we're dealing with numbers, which we often are. It's kind of a trade-off thing you have to decide, and I think I'm going to decide with the nicer API and less lines of code and faster-ish in some cases and not much slower in others. I mean, we are counting to, what is it here, 1,000? I don't know how long that would take. Additional. I mean, a real test would be like comparing an object or something that's much more complex than that. But all right, let's go crazy and let's reduce this by 1 and add this here. See what happens. Mm-hmm. It's faster still. So that is very interesting. Very, very interesting. How does this translate into code here? This compare value, this compare function, compare value is bigger than 0. Ah, well, there you have it. That's interesting. Are you seeing what I'm seeing? Ha ha ha. Well, TypeScript actually, when it transpiles to JavaScript, it actually does what we were doing by hand. Can that be? Am I seeing this right? Did I just copy the same thing, or? They look identical to me. They are identical. That is crazy. Let's just make sure that I didn't. So this is imp. Oh crap. What? No. How? What? It? How did this happen? Oh man. How did I do that? Oh. How did I do that? Got the compare function here. Got the compare. Yeah, it's the same thing. How did I? Whoa. Okay. That's some weird stuff. Did I copy the wrong thing somehow? Alright, let's change that, I guess. So what we want to do is current node. No, not current node. What we want to do is new node. New node. Oh, wait a minute. Yeah, okay. New node. No, that's not right. I'll do a new node is lower than current node. Alright, that's what we're doing here. Current node, yeah. And then we're doing if new node is greater than current node. Still interesting that there was a difference in speed if they were exactly the same implementation. That is really weird. Anyways, So I think we fixed this now. We are comparing two different implementations. Imp was our original one that uses our built-in compare thing. And this one is supposed to be the more optimized one, the comp. Yeah. I think I must have just, I don't know what I did, but okay. So now let's just get rid of this. Completely for now. And let us start with a smaller test. Okay. All right. Okay. The comp seems a bit faster. Yeah. Yep. Okay. Let's bump it up to our million. And now it isn't. Let's try it again. It runs a little longer. What would explain that? I'm curious to know. Like what? I just thought of something, because really, it's kind of silly, but we're not just testing. Let's look at it here. In doing this, we're not just testing this function. We're also testing the looping, the built-in JavaScript loop. And, you know, we're looping 3 different times, and for some reason the loop doesn't potentially run quite as fast from one time to the other for whatever reasons. So the correct way to test this, I've been doing this all wrong, I think. What would be the correct way to test this? The correct way to test this would be a bit more complicated, but we gotta do what we gotta do. Let's see here. Is there a way to add to, when we're doing console time, we are starting a timer that can be used to compute the duration of an operation. Timers are identified by a unique label. Cool. Can we stop the timer and start it again? Stop, start, stop, start. If we can, that would be cool. So console.time and stops the timer that was previously started by calling it, and prints the result to standard out. Time log for a timer that was previously started by calling console prints the elapsed time and other data arguments. Timeline, this method does not display anything. Trace. This method does not display anything unless the inspector count maintains an internal count specific to label and outputs the number of times console count has been called within the given label. Oh, That's cool. Huh, I didn't know console.assert. Alright, so if I do console.time, I think I want to read a little bit more about that. MDN console.time. Oh, which is kind of dumb because I'm using the nodes implementation, but whatever. Okay. The name to give to new, this will identify the owner. Use the same name when calling console and time end to stop the timer and get the time output to the console. Starts a timer you can use to track how long an operation takes. You give each timer a unique name and may have up to 10,000 timers. When you call console to time end with the same name, the browser will put the time in milliseconds that elapsed since the timer was started. Answer time, alert, click to continue, console time log, answer time. Will log the time needed by the user to dismiss the alert box. Yeah, okay. Don't care about stack traces. That didn't help me much. What I want to know is if I can start it up again. Mm-hmm. Well, there's groups. Okay, let's look at this. Creates a new inline group in the web console. This indents following console messages by an addition. Nah, that's not what I want. Oh my god, this is annoying. Let's pause notifications please. Thank you. Okay. Interesting. Let's take a look at nodes documentation, see if they have a different take. We've got console.time. It's about the same thing. Starts a timer that can be used to compute the duration of timers are identified by a unique label. Uses time label when calling console. Stop the timer and output the elapsed time in milliseconds. Uh-huh. Because what I essentially need to do, just trying to find an easy way to do this, but this is what I essentially need to do. Right? And I need to have something that's cumulative and start here and then stop there and then start here and stop there. Get the idea. But really, I mean, at the same time, we can probably trust that the implementation of the for loop is pretty consistent. Or can we? Well, here's an interesting test. Let's just do away with the loop altogether. See what we get. Item. So that would be items. Let's just grab the first one. Right. So in this test, the comp implementation is faster. Let's run it again. Still a bit faster. Let's run it again, but see how there's quite a bit of a difference. And we're just doing this one function here, which is just adding one thing to the root. So it's kind of weird that. And now it's faster by a bit more. Very interesting. And if I was to make this a longer running function, oh wow, okay, quite a bit of a difference this time. So, in the end, I mean, for, let's see. And we've got this running for, yeah, let's try this, see how long it'll take. Because I mean, in the best case scenario, which is pretty much the simplest compare function that we just had, a minus b, right? There's hardly a difference. But in the worst case, where it's a longer running function, it'll probably be, oh, it's taking too long. I'm not gonna wait that long. Let's go with this here. Should be better. A little better. There we go. 8 seconds for Basarats. Just a little bit longer for my BST comp. And a bit more for, you know, now what if we were to reduce the size of this, increase the size of that. Should be a little faster, I think. Yeah. It'll be interesting to see the difference. Not much of a difference, right? As the compare function gets longer and longer to run, the rest of the algorithm, and we can clearly see that as it gets longer, the comp implementation is faster. So I think I'm going to go with that. It's in the best case scenario where, let's see, the compare function is super simple. Get back here. Thank you. Don't need the return. There we go. Okay, let's run this. It's still faster, right? Yeah. Let's do it again. Well, not always. It's close enough, anyways. It's pretty much the same, because there's a little bit of variations here because of the for loop that's not running the same. Looks like it comes in a little longer, but I mean, we're talking like, you know, this one is a little, that's about a 1 millisecond. Interesting. Very interesting. Oh, so see, it's kind of a toss-up. But when we get into a compare function that's more complex, then it wins over. So I'm going to go with this implementation here, the comp implementation. Let's clean this up a little bit. And we've already determined that it's faster than our recursive option. So let's just rename that insert. That'll be our official insert function. And we will remove this. This will be our official add function. Like that. Let's just say that it returns void here. There we go. All right. I think that's enough for today. We've increased the performance a little bit. I'm not quite entirely satisfied with it, though. We are twice as slow as Basarat, so we need to figure out what's going on there. But that'll be for some other time. Thanks for watching. See you around.